Hello and welcome to part 2 of the forces lecture videos. So in the first lecture video, we learned about forces, what they are, the classification of internal and external forces, and we talked about the force of friction. Now in this lecture video, we're going to learn about adding forces and resolving forces. So starting with the addition of forces, the first thing that we need to know is that the net force acting on an object is the sum of all the external forces that are acting on it. Now, the sum is not a simple addition, though. We can't just add up the numbers that represent the sizes of the forces. The net force is the vector sum of all of the external forces. So this means that the full description of a net force includes its magnitude, so how large it is, and its direction, so which way is it acting in. And a force vector is also concerned with the line of action. So if you look at the picture here, the line of action indicates the direction of the force in a more absolute sense, right? Whereas the direction itself, this angle here, is relative to this unmoving reference, like this horizontal line here. So that's where the direction of the force actually is. Now, a force vector also has a point of application. So that's where the force is acting on the object. So in this case, the tail of the force vector touches the basketball player's hand, sorry. And that's where the point of application of the force is. So let's start with a simple case that involves what we call collinear forces. So collinear forces are forces that have the same line of action. Now the forces may act in the same direction or in opposite directions as long as they're along that same line of action. So if we take tug of war, for example, the rope is the line of action and the force that each player exerts on it is along this same line of action. So let's say that you're on a team with two teammates, and this is you over here. So you're pulling on the rope, with a force of 100 newtons. And your teammates are pulling with a force of 200 and 400 newtons. And you're all pulling along the same line of action, right? Along this rope here. So to find out the resultant of these three forces, we can start by just graphically representing all three forces. So first you would draw the 100 Newton force that was exerted by you on the rope. And then you draw the arrow representing the 200 Newton force from your teammate. And you put the tail of this force at the arrowhead of your 100 Newton force. So notice also how this arrow is twice as long as the 100 Newton as this first arrow. That's because 200 newtons is twice as big as 100 newtons. So remember that the length of the force vector has to do with the magnitude of the force. And then the last one is the 400 Newton force from the third teammate. And again, the tail of this force gets attached to the arrowhead of the previous force. So the resultant force, or the net force, must be 700 newtons acting towards the left, right? We've just added all three of these forces. And that's the same as calculating it mathematically. 100 plus 200 plus 400 is 700 newtons. Now, this is only true when the forces all act along the same line of action and in the same direction. So now let's look at the other team. That team also has three members, and the forces that they exert on the rope are all to the right, so in the opposite direction of your team, and they're each 200 newtons. So what is the resultant force, or the net force, of these three forces? Well, this is what the resultant force would look like here. So each of the members are pulling to the right with a force of 200 newtons. And that gives us a total resultant force of 600 newtons. Now let's put both teams together. So we want to know what is the resultant force acting on the rope as a result of your team pulling to the left and the other team pulling to the right. So the forces are all still collinear because they all act along the same line. They're all acting on that same rope, but the resultant is found graphically by adding an arrow from the tail of the 100 Newton force to the arrowhead of this 200 Newton force in the opposite direction. So that would be the resultant force here. So if we measured the length of this resultant vector, we would see that it's the same length as this 100 Newton vector, right? So the resultant force is 100 newtons to the left. Now, we could have also arrived at that same conclusion by comparing the resultant forces of each side, sort of mathematically, and it would look like this. So you add your three forces, and you're also adding the other team's forces, noting that they're in the opposite direction, right? And that again gives you the same answer, so plus 100 newtons, or in this case, 100 newtons to the left, towards your team. Okay, that was collinear forces. Now let's talk about concurrent forces. If forces do not act along the same line, but they do act through the same point, then the forces are called concurrent forces. Picture a gymnast who's about to start their routine on the high bars. After they jump up to grasp the bar, their coach stops their swinging by exerting forces on the front and the back of the gymnast's torso. So the diagram that represents these forces acting on the gymnast would look like this here. And this is called a free body diagram. Essentially, it shows all the forces that are acting on the system or the object, which in this case is the gymnast. So we assume that the gymnast is just one object or one system. So the external forces acting on the gymnast are the force of gravity acting at the center of mass of the gymnast. Then we have a horizontal force of 20 newtons exerted by the coach pushing on the front of the gymnast, and a horizontal force of 30 newtons in the opposite direction, and that's also exerted by the coach pushing at the back of the gymnast. And then we have this upward reaction force of 550 newtons, and that's exerted by the bars on the gymnast's hands. So if we know that the gymnast's mass is 51 kilograms, then we plug that into our F equals ma equation, and we find that the force of gravity is 500 newtons downwards. Okay, so let's do like we did before, where we assemble all of the forces from the diagram. So if we line up the forces tip to tail, we can find the resultant. So first we draw this 20 Newton horizontal force acting towards the right, and then we attach the 550 Newton force acting upwards from the bar, and you always draw it so that the tail of this new force begins at the head of the previous force. Okay, then we have a 30 Newton force acting towards the left or towards the front, and a 500 Newton force acting downwards at the head of this 30 Newton force. So you should have a drawing that looks something like this if you attach all of your forces together. And this is essentially just a graphic representation of all the forces that are acting on our system of interest, which is the gymnast here. So you'll notice, or hopefully notice, that the head of this 500 Newton downward force doesn't connect to the tail of the 20 Newton horizontal force. And the resultant force can be represented by this arrow that connects the tail of the 20 Newton force with the head of the 500 Newton force. So you make sure that you draw the arrow starting at the tail of the 20 Newton and going towards the head of the 500 Newton force. And this resultant force is directed upwards and slightly to the left, right? But obviously that's not precise enough. So to solve the resultant force, we need to break the forces down into their horizontal and vertical components. So horizontally, we have a force of 20 newtons to the right and 30 newtons to the left. So that gives us a resultant horizontal force of negative 10 newtons. Then we have a vertical force of 550 newtons upwards and 500 newtons downwards, giving us a resultant vertical force of plus 50 newtons, or 50 newtons upwards. And then to find the net resultant force, we go back to our mighty Pythagorean theorem, right? Because we've resolved our vertical and our horizontal forces, now we need to figure out the hypotenuse or the resultant force. So a squared plus b squared equals c squared. We plug in our numbers and we figure out that our resultant force is 51 newtons. Now, we found the magnitude of the resultant force, but we haven't yet determined what direction it's acting in. So now we use trigonometry to determine the angle of the resultant force. And that angle is what determines the direction of the resultant. So you've essentially solved all three sides of the triangle. You could use sine, cosine, or tan, any one that you wish to use. It doesn't matter. You'll get the same answer in the end, but I've used the tan function here. And my direction is 78.7 degrees above horizontal. And that's this angle here. So we've got our horizontal and vertical components that give us a resultant force of 51 newtons acting 78.7 degrees above horizontal. Okay, great. So to sum all of that up, if the forces are concurrent but not collinear, we can add the forces to determine the resultant force by graphically representing the forces as arrows and arranging them tip to tail. The resultant force will be represented by this arrow that's drawn from the tail of the first force to the tip of the last force. And alternatively, if the forces are directed only horizontally or vertically, then we can mathematically just add up all of the horizontal forces to determine the resultant horizontal force, and then add up all the vertical forces to determine the resultant vertical force. Also, the size of the resultant of these two forces can be determined using the Pythagorean theorem, and then its direction can be determined using trigonometry. Now, what happens if the external forces acting on the object are not collinear and they don't act in a vertical or horizontal direction? So in this case, if the object of interest is the shot or the ball being thrown, there's this vertical force from gravity acting on the shot, which is the weight of the shot. But the shot put thrower is also exerting a force on the shot, and that force isn't perfectly horizontal or vertical. The force from the athlete is pushing upwards and forward on the shot. Now, because this force acts to push the shot both horizontally and vertically, it can be represented by two different forces, a horizontal force and a vertical force. And those are the two components of this one force here. So let's start by looking at the problem graphically. So imagine that at the instant shown in the picture, the athlete was exerting a force of 100 newtons on the shot at an angle of 60 degrees above horizontal. And we also know that the mass of the shot is 4 kilograms. So let's first determine the weight of the shot or the force of gravity here. So by using F equals ma, we plug in the mass of 4 kilograms and the acceleration of gravity, 9.81 meters per second squared downwards, and we find the force of gravity is 39.24 newtons acting downwards. Now, we want to represent the 100 Newton force that acts forward and upward at 60 degrees, this one here above horizontal, as a pair of forces, right? The pair of forces that we're trying to find are called the horizontal and the vertical components of this 100 Newton force here. And the components here, you can think of them as the parts that make up a system. So in this case, the horizontal and the vertical force components of the 100 Newton force are the parts that make up this 100 Newton force. And we can think of the 100 Newton force as the resultant of adding the horizontal and vertical components of this force. So first, let's draw the 100 Newton force as a vector. Okay, so here's our 100 newtons acting at that same angle above horizontal. Next, think of how we graphically determined the resultant of two forces. We lined up the arrows representing these forces tip to tail, and then we drew an arrow from the tail of the first force arrow to the tip of the last force arrow. And this last force arrow we drew was the resultant. Now we want to work that process in reverse. So we know that the resultant force, we know what that resultant force is, but we want to know what horizontal and vertical forces can be added together to produce this resultant. And the easiest way to do this is to draw a box around the 100 Newton force so that the sides of the box align vertically or horizontally, and so that the 100 Newton force runs diagonally through that box from corner to corner. So here's the box running from corner to corner, right? The resultant force. Notice that the box is actually just two triangles with the 100 Newton resultant force as the common side to both triangles. In each triangle, the other two sides represent the horizontal and vertical components of the 100 Newton force. So in the upper triangle, the 100 Newton resultant force is the outcome when we start with a vertical force, start here, and we add our horizontal force to it. The triangles are identical, so we can use either one. It doesn't matter. Let's just use the lower triangle here. So next, we need to put arrowheads on our components to give each of them a direction. So we've got our resultant force. Then we add the horizontal component with an arrowhead in that correct direction, and then our vertical component with an arrowhead that eventually meets at the arrowhead of the resultant force. So this represents our horizontal and vertical components to this one horizontal or resultant force here. Okay, so the process of determining what two force components add together to make a resultant force is called force resolution. So we resolved a force into its components. And the word resolve sounds like resolve, which is exactly what we did. We had the resultant force and we solved the problem backwards. We re-solved it to determine the forces that added together to give us our resultant. So far, we've only done this graphically, and that will only give us an estimate of the magnitude of each component. So now we want a non-graphical technique or a mathematical technique for resolving forces. So the force triangle that we ended up with is this right angle triangle. And again, we know that the resultant force is 100 newtons acting upward and to the right, 60 degrees above horizontal. And the 100 Newton force is the hypotenuse of this right angle triangle. So the horizontal side of the triangle is the side adjacent to this 60-degree angle, which means that we can determine the length of the horizontal component by using the cosine function. So using the cosine function, we determine that the horizontal component of the resultant is 50 newtons. And next, we need to solve the vertical component of the force. So this time we use the sine function because we're looking for the opposite side of the triangle. And we obtain a vertical component force of 86.6 newtons. So we can now determine the net force that's acting on the shot by adding up all the horizontal forces to get the resultant horizontal force, and then adding up all the vertical forces to get the resultant vertical force. Now, in this case, the only horizontal force that's acting on the shot is the horizontal component of this 100 Newton force. So that means the net horizontal force is 50 newtons. But there are two vertical forces that are acting on the shot. You have the weight of the shot, right? The force of gravity, which is acting downwards, 40 newtons downwards. That's this force here. But we also have our vertical component of this force here, which we calculated to be 86.6 newtons upwards. So if we add those two vertical forces together, we get a resultant vertical force of 46.6 newtons upwards. or plus 46.6 newtons. Okay, so using the Pythagorean theorem first, we can then find the net force that's acting on the shot. So the net external force acting on the shot in this case is 68.4 newtons. And then to complete the problem, we also need to know the direction of this net external force. So then we use trigonometry to determine the angle that the net force is applied at. And the force triangle is made up of the 46.6 Newton vertical force, the 50 Newton horizontal force, and the recently calculated net force of 68.4 newtons. So we can, again, use any trigonometry function to find our angle here because we have all three sides. I've used tan and get an angle of 43 degrees. So the net external force acting on the shot in this case is a force of 68.4 newtons acting forward and upward at an angle of 43 degrees above horizontal. We made it! So that's it for the second forces lecture video. In this video, we learned how to add forces and how to resolve the force vectors into their individual components. We've got one more video for the forces lectures.